my job today, remove fear of mathematical equations. um, so I'll use the basics neural network. How's it related to? And we'll start with people connected net, multi-layer perceptions. Start with that, and then we'll move on to potential RNN, the vanilla RNN. I won't go to LSTM, and I'll jump into attention-based model. Attention, multi-headed, wide attention head, narrow attention head. So we're gonna look at mathematical, but simple. So that's the gist of what I say. Feel free to stop me if nothing, or if anything. Hopefully it's making sense. Hopefully it's not the case that nothing is making sense. So if you have any problem, just let me know. Firstly, we all know what a neural network. Yes. And do we understand what happens within a neuron? So what's happening inside a neuron? Try a new page. Let's try a neuron. Okay, so this is the circular thing that you have seen in the previous slides. Neural network takes in input, do some transformation, and produce an output. Okay, so that's a simple summary of the neural network. So let's just take a closer look at what's inside this circular neuron. Yeah, so the neuron actually takes in a lot of input. So you have input goes from your X1 and your X2, X3, and so forth. You might have X4 and all the way to Xn. Okay, so let's say we just have 3. So my input is also represented as a circle inside a circle. So I have X1, X2, X3. So these X1, X2, X3, they're all scalar values. They're numbers. Okay, so this number got multiplied by some weight. So I might have, if this is my neuron 0, so I might have 0, 1. So I should start from 0 just for mention. So 0, 0, and then 0, 1, 0, 2. So these are 3 different ways connected to this hidden layer, the first neuron of the hidden layer. And the first thing it does is it sums things up. Okay, so it sums the input, this weighted sum of your input up, and then it does some kind of what you call it as activation. Okay, so the activation could be doing a job of squashing between -1 and +1, or squashing between 0 and 1, or only preserve the positive value and then discard all the negative values. So that's called ReLU. Depending on what your activation function is, your output might be within certain different range. So we have an output coming out of the neuron like this. How do we express this mathematically? what we tend to do is maybe we could do W00 x0 plus, because we're doing weighted sum, and then we apply, so in this case is -1, +1, then the function, the activation function is 10h, hyperbolic 10. And this gives me a output value. Okay, so I have an output value coming out. Let's say, let's call it y. Y comes out. Right. So how do we do this a bit more succinctly in math? If we treat the input as a vector, so have a look that this is my vector. My vector inputs as x0, x1, x2. And this becomes a dot product, right? So it will be x transpose times, or not really times, but gives you the vector of W0. Right, so I have, let's make this bold. And this gives me a single value y. And imagine if this is only one neuron, right? We have multiple neurons. I might have neuron, I have another neuron 1. Yeah. Oops, sorry, the drawing circles. A neuron 1 here, a neuron 2 here, and I still have the same input. And fully connected with all these neurons. Every single neuron is doing the same job of summing the input up and do a nonlinear transformation. Summing the input and do a nonlinear transformation. How would your function look like? So we're going to have a xt, but instead of just having W0, now we have a matrix. Okay, so this is a 1 by, this is let's say 3 by 1. 1 by 3. And this is going to be 3 by, if my output is 1, so this is going to be 3 by 1, but if my output is 3, then it will be 3 by 3. Okay, so this gets dot product with W0, which is the first neuron, and then W1 and W2. Okay, so this, every single line will have the weights there. This will be 1, 0, and then 1, 1, and then 1, 2, and so on. Okay, so now you have a matrix of 3 by 3, and then what you get output is every single neuron will give you a y. So this is y0, y1, and this is y2. And these neurons, this neural output from each of these will be added up together, go to another neuron. So that's the output layer. Okay. Again, then you have weights here and weights here, weights here. Okay, so then this would be that's 1, this is 1 0, 1 2, and then 1 3. Or maybe you shouldn't use W anymore because this is output layer. I think my notation was slightly different from the lecture notes. The lecture notes says the first input to hidden layer is going to be U, and then the output layer would be W. Okay, so you use W instead of U, so for less of a confusion. So here will be U0, U1, U2. But no matter what you do, it's turning this neural net into a matrix multiplication and then apply a nonlinear transformation and give you a set of output. So this set of output is Y0, Y1, and Y3. And this will go out and gets multiplied by the weights to give you another final output. So if I have the sigmoid in as the squashing function or the activation function, you get a probability because sigmoid would take in any value and then squash it in between 0 and 1. Right, okay, so back to this. Then these slides will become hopefully slightly better to understand. So we said a vector of input nodes will be something represented like that, and then you use a hat arrow with an arrow to indicate this is a vector, not a singular, not a scalar value. And then you have the hidden nodes, and then the output nodes, each of them represented as vectors. Okay, so the values that you work alongside the neural network are basically a vector multiplied by a matrix to give you another vector. So that vector could be a hidden layer vector or multiple hidden layer vectors. And then finally, you get an output vector. Okay, so to put it as a simple representation, we said the matrix of weights connecting the input nodes with the hidden nodes is using a notation U. And then the matrix connecting the hidden nodes with the output nodes is using a matrix W. Okay, so the hidden vector is an input multiplied, so your input vector multiplied by the weight matrix U. And then this same hidden vector gets multiplied by the weight between the hidden nodes and output nodes to give you the output layer. So this is a simple 3-layered network. You have one input layer, one hidden layer, and then one output layer. So that's basically a very simple mathematical notation that's making use of vectors and matrix multiplication. However, this, as you can see, that this is basically just linear combinations, and that linear combination doesn't really make your life any more challenging because you can basically just do the multiplication all the way together. You don't really have any surprises. Okay, so it's just linear transformation, which weighted sum of your input. Do you remember anything that any model that is doing the weighted sum of input? Is there a machine learning model that you can think of that's simply just doing linear weighted sum and you learn the weight? You guys all have done machine learning. Sorry? Yeah, logistic regression is a generalized version of linear regression. So if you just have the linear combination of inputs, that's just linear regression. Okay, so logistic regression is one step further. it's generalized linear regression. So if we don't add any activation function, no nonlinearity, we're basically implementing a, so if we don't have this nonlinearity, we're basically implementing a linear regression. So linear regression can be represented as neural network if you want to. But basically you said, you know, your activation function is just a mapping of whatever your sum is multiplied by 1. So it's a constant. So your activation function could be a constant. Just all the time is 1, no matter what value. Oh, sorry, it's not 1. It should be, so it should be a bit like value. It's the whatever input is. If your activation function is this diagonal line of y equal to x, right? So whatever the input is, and it goes out. So no nonlinear squashing. Then you have implemented linear regression using neural net, right? Make sense? Yeah. So the activation function, if you design your activation function to be y equal to x, then we don't really have nonlinearity. We basically implemented a linear regression problem. So all this neural network, these nodes connection, are just visual candies. So visually, you treat that as a neural net, but effectively you're just doing matrix multiplied by input vector, apply a nonlinear transformation, you get a new value, and that new value gets pushed down into the next round of transformation. Okay, so I have slides on how this actually worked. So if you have let's say 0 and 1, so this is a neural network trained to learn a function called exclusive OR. So you could say, okay, if I give a training instance 0 and 1 with a bias or with a constant as a bias input to a 3-layered neural net where the hidden layer has 3 nodes, so 2 active nodes and then 1 bias nodes. And then we have the output produced as a single value. So whether 0 and 1 gives you 0 and 1, so in exclusive OR. So if we have 0, 0 and 1, 0 and 1 gives you 1, and 0, 0 gives you 0, and then 1, 1 gives you 0, 1, 0 gives you 1. So this function basically can be trained to learn to perform like an exclusive OR. And then after all your training, so you can see that the summation going is the weights, assuming that we have initialized with some random weights. So the weights times the input. So 1 times h0. Okay, so this is 1, 0. So the input is actually 1, 0. 1, 0. So the 1 times 3, okay, goes in here. 0 times 4 goes in there. And then 1 times -2 goes in there. And then we apply sigmoid of 1, then we get 0.731. So this will be 0.731. And similarly, we'll get 0.119. And then they get multiplied by the corresponding weights. So 0.731 times 5 and 0.119 times -5 plus this bias in the hidden layer, then we get a final output y0. And you notice that this y0 can be any value. It doesn't have to be between 0 and 1. But once you apply sigmoid, it squash it between 0 and 1. That becomes the probability, because this one is fairly close to 1. We'll treat that, if we apply a threshold, we'll treat that as a correct prediction. Okay. And then the error gets back propagated through a much involved process of back propagation, which requires partial derivative on the weights. So that little changes is how much nudge or nudging you want your weights to adjust for every single weight. Okay, and then the mu here is a learning rate that you can apply. So as soon as you go through one sample, one input, which is 1 and 0 in this case, then in terms of back propagation, you can adjust your weights. And then in the training, you have something called batch and mini batch. So this is related to how many samples you need to train before you do the update of the weight. So batch is when you have all your entire data set to go through your system, and then you do the updates only once the entire data set, the entire batch gets through. So that's going to give you very smooth learning, but it's gonna, especially with large data sets, you don't want to feed an entire batch into your learning system. That's firstly, your memory probably won't allow it. Secondly, your learning is going to be super slow, that you're not adjusting your weights sooner enough. And then with mini batch, typically the number you set is seeing 64 or 32 instances before you do an update. Okay, so batch processing, mini batch is to do with how much data instances you use for a single update of your weight. Okay, I won't go into the detail of loss functions. We will move on to the RNNs. Okay, so what does RNN do? What does it look like? So there's something called Elman RNN, which is basically a way of saying this is vanilla RNN, the simplest RNN that you have. And then you add in forget gate and then update gates, etc., to make it into LSTM and GRU. But we won't really go into that. Let's just look at the Elman RNN. So with recurrent network, it's similar to feed-forward networks in the sense that it's a neural network model. Again, the neural network is a candy, an eye candy. So let's just try to think of that as matrix manipulation. So the other term that I forgot to mention is when you do the weighted sum of your input, that linear combination is called a affine transformation. So if you see someone using the word affine transformation, it's just a fancy way of saying this is a linear combination of it, okay, a weighted sum of it. With Elman RNN, we could start with a hidden state. So a initial hidden state could be just 0, 0 if you have 2 inputs, okay? But you have this structure that keeps rolling or repeating itself. Okay, so you have a concept called RNN cell. This RNN cell will work on your input. Okay, so your input, remember your input is a sequence of values. So your first value could be the one that we have is 0, the XOR, right? So let's say the first value is 1, and then the second value is 0. So that's a input instance. With that vector, that input vector of 0 and 1, 1, 0, we can have two RNN cells. So you start with the input, which is x0, and then you initialize a hidden state, and that hidden state can be of different dimensions. So my input could be 2 dimensions, for example, or 3 dimensions. My hidden states can be 5 or 6 or d dimension. They don't have to be the same. Okay, so the dimensionality can be different. Okay, so so I still haven't really say what's going on within that RNN cell. But what it does is, let's go into a slightly more involved cell, which is basically now becoming the weight of transformation. Okay, so you can see, let's say your x is 2 dimension, and then it multiplied by a weight matrix, and then your hidden state gets multiplied by another set of weights, and then they gets added together, and then you go through a hyperbolic can, and then you produce another hidden state that goes to the next cell, right? And then your output can go from this cell as well. So how do we do this or imagine this mathematically? So here the x is an instance, is a vector. It's not a single value. So if I have a 2-dimensional input, my x will be a vector of say a vector of 1, 0. Okay, so this x is a vector. And the reason why it is useful for natural language processing is this could be the vector representation of a single word or single token. That could be another word in a sentence, and you can just keep going on. So you have you might have another vector for x2 and another vector for x3, and depending on the size of your sentence, you can have a sequence of RNN cell. You basically write a for loop that contains multiple RNN cells based on your sentence length, your maximum allowed number of words in a sentence. Right. So when we have this input come in, we have the hidden state, which has the weight called hidden to hidden weight. And then this weight here is the input to hidden weight. So imagine that your input is, let's say your input is m dimension, and then your hidden state is d dimension. You're trying to get let me see. You're trying to get a output, a single valued output, then you will have to work out the dimensionality of your matrix, right? So try to example. So where, let's say my m is equal to 2, and then my hidden state is 3, And then in order to make sure that this turns into the same dimensionality, that I can add them together into a vector. So I will do, 1 times, so 2 times 1, transform, you give me 1 times 2. So this is 1, 0, 1 times 2. And then this one will be 2 times 3. So I can get a vector of 3 elements. Okay. And then this input hidden state, because it has 3 values, 0.1, 0.3, and 0.1 again, that's my hidden state or vector. And this will need to be transposed and then multiplied by a 3 by 3 matrix, which is my WHH, and this is my WIH. WIH is 2 by 3, and WHH is 3 by 3. So again, this gives me a 1 by 3. So in this case, if I write it that way, so 3 by 1, 3 by 1 vector. Okay, so this is your control of the dimensionality. So as when you do your programming, you need to think about all the transformation, all the dimensionality that you need to work on. So once we have that, it becomes mathematically quite easy to express. So we have the previous hidden layer or the hidden state, the previous hidden state multiplied by the hidden to hidden weights plus the bias, we give us the next hidden state vector. Sorry, not the next hidden state vector, but we prepared contribution of the hidden state to the next hidden state vector. And then we have the input transformed through an input to hidden state matrix. And then we prepared a vector of the same dimensionality as, so Tx, the transformed input and the transformed hidden state will have the same dimensionality. And once we have that, we turn that through a activation function. So in this case, we choose most of the vanilla RNNs is using hyperbolic 10 to squash it and giving me the next hidden state. Okay, so that's what's going on within RNN cell. The input gets transformed, and then the hidden state, the previous hidden state gets transformed. Add them together, go through a hyperbolic 10, you get the next hidden state. That makes sense? So the difference between RNN and CNN is the weights. Even though you're rolling from one RNN cell to the next state, the weights remain the same set of weights. So every time you just update the same set of weights, you don't learn new weights. But in CNN, every single convolutional block, you have a new set of weights. So RNN is computationally considered to be cheaper as compared to CNN, but CNN is faster in the sense because you can run things in parallel, where RNN you have to always wait for the previous cell to finish compute before you move on to the next cell. So RNN is, even if you have GPUs, you can't really leverage the parallel compute power offered by GPU. So RNN is not computationally friendly because every time you have to wait for the previous one to finish before you can compute the next one. Okay, so input transformed, hidden state transformed, added up, and then you get, and then apply a activation function, and then you get the hidden state. Okay, is this too boring? Yeah, it's okay, or Mhm. Right. Fast forward to attention mechanism. So um, certainly paying attention is like a human behavior, right? So when something is important, we'll pay attention to it. And in neural network, we also want the attention to be given to the right region of the image or term of the image. Then we'll have a better output, in the sense, if we want to translate the word European we into French, we will concentrate on the, I can't really pronounce that, but the corresponding French way of saying European. And similarly, the economic zone should be more closely related to the la zone economic, that's in French. So you pay attention to certain area of your token sequence. And so when we try to visualize that in a matrix, we can see, when we see the words la, then the English translation the should have a higher weight. And then because la is in French, you have a feminine noun and masculine noun, and so that LA is corresponding to or modifying the word zone as well. So that's why zone has a 0.2 attention score. So we want to build a system, build a learning architecture that allows us to work out these attention scores automatically. So in the encoder decoder framework, where you encode the input and then decode into a different output. So let's say we are translating from English to French. What we're doing is we encode the English, and when we do the decoding, we try to predict the French counterpart of that English sentence. And similarly, as you can see in lots of sequence to sequence learning or encoder to decoder framework. So sequence to sequence assumes your input is a sequence, and then output is also a sequence, right? And then you have input is image, and output is a sentence. So if we do image to sequence, what kind of task can you think of? Image to sequence. It's also an encoder decoder model, right? But you just encode the image, and then the decoder will give you a sequence, right? So encode the image and decode into a sequence. Given an image of a cat, or you can't really draw a cat, image a cat, and then this is your encoder decoder model. And then you give some sequence out, okay? So the sequence might say the cat is sat on a mat, or the cat is in a box. This is called image captioning. right? So image captioning is modeled as an encoder-decoder task. And this image could be a video. So the video to sequence is video description task. And now what ChatGPT is doing is that you give the other way around. So you have a sequence to image task. So we give the sequence and then we use the decoder to generate image. That's what a lot of the multi-model large language model do. You give prompt text instruction and then it generate image. So really it's pretty much nowadays, if we say encoder decoder model, we could do anything to anything or whatever to whatever, right? So you could have a combination of images and text and videos to generate images or generate text, and generate sentences or descriptions and audio and etc. So this is the generative AI, which is leveraging a encoder decoder model. And sometimes you don't have to have the encoder. So the GPT, what does GPT stand for? So the generated pre-trained transformers, what it does is it takes in a input, it will just keep generating the text. So it's purely just a decoder. It's not, it doesn't even require a encoder. But still, I mean, this architecture of encoding, decoding is very generic, and you can see it in many different deep learning representation learning papers. Okay, so, but the encoder, decoder, the encoder does not have to be transformers, and decoder doesn't have to be transformers. Encoder can be, in this case, RNN or CNN or P3D, so whatever model that you think is relevant to your input type or effective to your input type to capture the features. So what we have here in this blue box is a RNN encoder. Okay, so the input of 2 words gets going into a RNN layer which contains 2 RNN cells. Because my input sentence is only 2 words long. And then I take in the input, the initial hidden state would be anything randomized, randomly generated. My hidden state goes in, triggers the first RNN cell. Remember that this RNN cell just basically does a input transformation. It basically just does an input transformation plus a hidden state transformation, add them together, goes through a 10H activation function, and then they produce my next hidden state. And this next hidden state gets transformed together, add together to the transformed input, and then goes through a 10H and gives me the final hidden state. Okay, so this final hidden state encodes what's inside these 2 words. So that hidden state gets pushed into a decoder. So this decoder goes through the same thing, but once it goes through the same RNN cell with a different set of weights, combined with a random starting token. So this starting token is basically telling the system, now my decoder's job starts. Okay, so this start token could be a new token. It could also be the last token of the previous sentence. So this token, together with the final hidden state, each gets transformed through a set of weights. Remember, all those set of weights needs to be learned, and then go through a 10H, and then they produce a H2. The same H2 is not only used for input as the next cell, but it's also used for prediction task. Okay, so this prediction task goes through some hidden state, and then this hidden state is used to be multiplied by another set of weights, which is something that you need to learn, and then predict the corresponding token in the target language. Okay, so you can imagine that this transformation could go through some sort of softmax. Softmax allows you to predict multiple distribution of multiple potential labels. So in this case, if I just have that example here, how many words do I have in French? So 1, 2, 3, 4. So I might have a vocabulary of 4. Then I have a 4 class classification. So I want to say, okay, so the 4 class classification, the first word is la. So it'll be 1, 0, 0, 0. If I use one hot encoding, so this is la. And then zone will be 0, 1, 0, 0. Right? And then this economic in French will be 0, 0, 1, 0. So basically only the position of that word will have a 1. So this is one hot encoding. So you have 0, 0, 0, 1 for European, the French way of saying European. So what this one does is basically using softmax to produce a vector to see how close it is to the one hot encoding of la. So imagine if I do a really good job, I might have 0.7 here, 0.2 here, 0.1 here, that's already 1, and 0 here. So that's what softmax will give me. Give me a vector of this, and then I compare these two vectors, either using cosine similarity or using Euclidean distance or Manhattan distance or some other distance that you can define to work out the loss. Okay, so that loss will come back and change this weight, change the weights in here, change the weights in there, change the weights in there. So your whole system gets updated according to whether you are predicting it correctly or not. Okay, once you generate that word, your system is still going on, right? So your H2 will go to the next cell, and then go through that transformation again, and then do a softmax, and then predicting the next word. So the process just keep going on if you have like longer sentences. That's what the encoder-decoder, how the encoder-decoder works. But the thing I haven't really talked about right now is what exactly is this attention mode? Okay, so we haven't really touched on the attention mechanism here. So we don't really know whether I should put more attention on in order to predict the la, should I put more attention on the, or should I put more attention on zone? Okay, so this is achieved through this attention mechanism. So the attention mechanism basically takes in the hidden state from the first cell, takes on the hidden states of the second cell, and then work out a weight. So that that weight is basically saying, okay, I should put 80% of attention on the word the and 20% of attention on the word zone. So how do we work out these attention scores or attention values? This is done through the QV, was it, sorry? Oh yeah, sorry. The QVK, this is the query, so just keep in mind this is the query. And then this hidden states gets transformed through a fine transformation to get a key value, sorry, to transform into a key vector, and then gets transformed to a V vector, and then this H20, H21 gets transformed into a Q vector. And then we work out to see whether the question and the key matches each other. How much do they match? So, and then we put that how much against the value. So that how much is 0.8, and then we take 0.8 times this value to push that across into the next state. Okay, so that will become slightly clearer if we can do a bit size on that. So the context vector, as I said before, what you need to work out is the alpha 0 and alpha 1, okay? And then the alpha 0 and alpha 1 gives you the weighted sum of the two hidden states, and that push on to the next one. This diagram, we have a picture. Okay, so here's the picture that I'm looking for. So you see that your hidden state with a two-dimensional, so D equal to 2, a very simple small dimensionality for the hidden state. So the hidden state has 2 dimensions, and then it gets transformed through a set of weights to give you K, right? And in this case, it didn't really transform it again to give you V, but in the implementation of transformers, the value never gets straight away extracted out of your hidden state. It gets transformed again. So there's a transform here. So this is the value transform. And then this is the K transform. And then again, you see the Q. The Q is a transformation from the decoder's hidden state. Okay, so these W are all different. So this W is a 2x2 matrix. That's a 2x2 matrix. That's a 2x2 matrix. Altogether, we have 4 weights here, 4 weights here, 4 weights there. So 4 times 3 because we have K, B, Q, 3 different types of transformation. Okay, so these transformations allows you to compare the Q with the K to work out a scalar value, and this scalar value multiply the transformed value and then give you a alignment vector. So that alignment vector combined with the other input sequence added up to give you a context vector. And then this context vector gets concatenated with the hidden states predicted from your decoder, and then gets transformed again, and then do the prediction of what the next word is. Okay, and then this predicted next word could be used as the input for another hidden, not hidden, another RNN cell in the decoder. So there's a concept of teacher forcing. So the concept of teacher forcing basically says, I already know what the next word should be. So for my second RNN cell, I'm using the known token rather than the token that I predicted, because the token I predicted may be wrong. So the teacher forcing sometimes performs slightly better, but you don't want to throw away all your learning as well. So typically there's a probability value that you set here to say, how many times I use teacher forcing, what's the frequency I use teacher forcing, and what's the frequency of using the previous predicted value. Any questions? Is it all making sense or not? Yeah. Mm. 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 If the translation has 3 words, you just keep adding. Yeah. So for example, if we have a 2 words predicting 3 words, right? And then after this x2, I don't have a teacher forcing. I could, because in my we call it parallel corpus, in my ground truths, I have the third word, right? So if I have the third word, I can still make use of teacher forcing. I just basically have another RNN cell without stopping. Okay, so you make use of your ground truths to give you a for loop length of how many words that you want to predict. And if you don't, you can set a maximum number of words that you want to predict. And then it will just predict, for example, if it should be empty, I'll just predict an empty blank pad. So you can introduce special tokens, for example, blank. So if you predict a blank or you predict and, this thing should stop. Yeah, it's fine. No questions online? Hmm?
They're asking is the iPhone what do you
Yeah, you use the probability. So you define a probability. I mean, it's a hyperparameter. There's no good. It's very case based or task based. There's not a single value that's best for setting that probability. Okay, so okay, so this one I use RNN as encoder, and bear in mind this encoder can be anything. Can be, MLP if you want to. Or 1D CNN, but no one is using it in that way. Okay, so a scoring function which gives you the scores between the key comparison with the question, right? So then so you can see that we typically could do cosine similarity. So the k, as both k and q are vector of the same dimension because they're the same size of the hidden state. The cosine similarity is probably the most natural way of measuring their similarity. And then because the cosine similarity does not consider the magnitudes of the vectors, we could use the dot product, okay? So we want to take the magnitudes into consideration. What we tend to do is just q dot k, but most of the time we would normalize that by dividing the square root of the dimensionality, because we don't want the high dimension to take more advantage. So I think, yeah, this is very, so this is the scaled dot product. So this is something gets used very often. So it's similar to the dot product, which is this one, except for a scaling factor. So this scaling factor is the square root of the hidden state, the dimension of the hidden state. Okay, so that this one gets used very often, but you can see there are other ways of working out the alpha 0 and alpha 1 in this case. I think it's called the attention scores, which is typically used as a way of producing a weighted sum of the value. Okay, so what I said before is only one head. Okay, so imagine that if you duplicate the process into a second head, you have another set of weights against everything. So here you see the weights, the second head, which is that one here. Okay, so the second head has a new set of weights. So previously we have 4 by so we have 4 for the for each VQ K, and so 4 times 3. And if you have 2 heads, then you have 3 times 2. Oh, sorry, 3 times 4. So 3 times 4 is one head will have that many weights, and then you times 2. That's 2 heads. Okay, and then if you have n heads, then this number of heads could be quite big. And there's a research paper in MLP back in almost 10 years ago, 2000, talking about how each head is capturing different linguistic characteristics of a language. So one head might be focusing on the grammatical correctness, and then another head might be focusing on the what do you call it, the lexical meaning, and then another head might be semantic meaning. So linguistically, there's a investigation on the information captured by this attention head. Okay, so a simpler diagram here. You have the query, you have the key, and you have the value. Each goes through multi-heads of linear transformation. So the linear transformation is the affine transformation, right? So, and then this this stuff goes through the scaled dot product attention, which is basically k dot q divided by the square root of D, which gives you the attention scores. And then the attention score gets multiplied by the V, and then you concatenate multiple heads together, and then go through a linear transformation again. Okay, so I won't really, when you have large dimensionality, you could break it down. So for example, after the transformation, you have input is 4 dimension, and then after the transformation, you still have 4 dimension, but you can break it up into 2 lots and then go through the transformation separately. So with different attention heads. So this is called narrow attention with 2 heads. If you previously, what we're doing is all the transformed vectors, the entire transform vectors, regardless of how many dimensions you have, will be going through the same heads. But now we could have them split up into multiple attention heads. So this is called narrow attention. So really, I mean, when you look into this, I hate to say that it all depends on your imagination. There's no justification why you would use narrow attention against a broad everything attention. Okay, and there's no justification on how many heads that you need, which is again, so this is the art of design a neural network. It's an art, it's not science. You don't have correct, right or wrong answers. So here's some intuition. It says the wide attention, likely the pros of wide attention is likely it yield better models as compared to use narrow attention, because everything gets captured in your hidden state, all the features captured in hidden state are kept succinctly in one vector and gets compared to the rest of the vectors, the query vectors. But it cannot deal with large dimensions. And then the narrow attention is only useful when you have really large dimensions. But because the broken down is almost arbitrary, it may not capture the information properly. However, transformer uses narrow attention. And just imagine that the current large language model, what's the dimensionality of the, no, that's BERT is 768, and then GPT might 1000, and then the current Chat GPT, the OpenAI GPT 3.5 and 3.4, I think the dimensionality is about 10,000 or even 12,000. I can't remember. I read it somewhere. Yeah, so it's the vector dimension in current large language. How am I going on time? Okay, so we've got this all kinds of attentions introduced, and then yeah, so this is mathematically how it works out. Our once we've done the dot product divided by the square root of the dimensionality, we get a softmax. Softmax guarantees that these two values add up to 1. Okay? and then you get the context vector multiply the value, multiply the values, and then we get the new value to be appended, the context vector to be appended with the other heads, with other multiple heads before you move on to the next set of calculation. I won't really go into the code, but how's this get all into have self-attention? Okay, so self-attention is, instead of using the decoder's hidden states transformed, so the transformed hidden states from the decoders, we, as queries, we can use our own inputs to query ourselves. Okay, so you can see this input vector gets a fine transform 3 times. One is generating a K, and the other one is generating a V, and then another one is generating Q, and then go through this same KQV mechanism to do a context vector generation. Okay, and with an attention score. So this not only applies to itself, it's also applying it to to other tokens in the same same sequence. Okay, so you can think of that as a pairwise comparison of every single pair in your sequence gets compared and transformed and goes through this attention mechanism. So that's what self-attention does. So self-attention is a very expensive mechanism because every single pair in your sequence gets compared with each other for calculating the scores, calculating the attention scores. Okay, so with that self-attention in mind, coupled with 2 things, one is the position encoding, and the other one is the layer norm, then we get a transformer. Okay, so I wouldn't go through the positional encoding, because once you have your input into a self-attention block like the like this, you no longer have a sequential information captured. You don't. So this could be any word, and this could be any words in that sequence. The ordering is gone. How do we get the order back? We use something called the cyclic position encoding. You want me to go through position encoding, or can just treat that as a function? Anyone wants to know position encoding? Yes? Okay. Okay, so how do we encode the position? So if we have position, let's say if I have 4 elements in a sequence, right, 4 words in a sequence. The first option could be I just use a modular by 4, okay, or divided the position number divided by 4, right? So we can normalize the indices. So 0, 1, 2, 3 are my indices, and then I can normalize the indices by fixed length. I'll just use, so in this case I choose 4. And then I have 0, And so the 0 position corresponding to 0, the 1 position corresponding to 0.25. So this 1 over 4, and then 2 over 4, and then 3 over 4. Okay. But then it won't really scale, because with a longer sequence, here I have 8 words, right? With a longer sequence, I already generating values that's larger than 1. And this becomes unpredictable. As you can see, throughout the entire neural network journey, we want to squash the value. We want to make sure the value is within certain range, so that my learning is always predictable within that range. So any value that's beyond the range of -1 to +1 becomes less controllable. So we don't want the values for longer sequences to give me a position value larger than 1. And then another possibility is normalizing the indices by its own length. So rather than have a fixed integer 4, I can divide by the length of that sequence. Okay, so if I have a 4-word sentence, and then 4 could be used as the denominator to normalize my position. And then if I have a longer sentence with 8 words, then I can use 8 as the denominator. So, but the trouble is, you see the position 1 doesn't have the same value, right? So position 1, in the case previously, position 1 is always, 0.25, and position 2 is always 0.5. But in this case, the same position, because I normalize it with the sentence own length, even though I meet the first criteria, the value is no longer larger than 1, but the same position doesn't give me the same position. The same index doesn't give me the same position value. And then another option is, well, you can potentially take the modular. So then it's kind of repeating itself. Okay, so if we take the remainder, it's repeating itself, which means that 2 positions or even 3 positions will have the same position value. So then your normalized position is no longer unique. It doesn't really uniquely identify the position of the word in your sequence, or the position of token in your sequence. And then there's people coming up with builds, instead of having a single value representing the position, how about we build 3 vectors instead? And then we can use any hypothetical sequence length, right? So we could use, this modulus of 4 and 5 and 7. So we obtain a vector to represent that position. And so this solves the problem of that position 0 and 4 are no longer the same as what we had before. Okay, so we solved the value that is unique up to the combination of all your denominators. So this 140 is 4 times 4 times 7. Okay, so depending on, and you could just keep going. So in order not for it to repeat itself, I could choose a 9, I could choose a 11, and then I become the position vector is going to be 5 dimension long. So each position will have its own unique position vector, up to 4 times 5 times 7 times 9 times 11. Okay, so if you have that many positions, then I mean, very unlikely you have that many positions because your sentence wouldn't be that long. I think just 140 is already good enough because typically you wouldn't write a sentence that long. But if you use this for other things, maybe protein, I don't know, the longest protein sequence, how long that could be. But that's the good news. Now we solve the problems of uniqueness, but we don't have a position difference maintained. So between, let's say this is only 2 tokens. So these 2 tokens next to each other, right? So I have token 2's position value, take away the token 1's position value should be equal to any other, adjacent tokens position value. So the 6 and 5 value difference should be the same as 2 and 1 because they're all next to each other. Okay, but we don't really have that property if you're using just randomly chosen 4, 5, 7. So now we move on to a encoding scheme that is using a smooth circle. So this circle, if I have a base 4, I work out the the circle with 0 degrees, 90 degrees, and then 180 degrees. So the second one is 90 degrees, and then the third one is 180 degrees, and then 360 degrees, right? So this is divided by 4, and then it repeats again, right? So, but then I have 2 values. I take the sign of 0, and then the cosine of 0 to get this vector for base 4, right? And then I could have base 5. So every time you just move, how many, what degree is this? So 360 divided by 5, 75 degrees. And then you could have base 7. So it's 360 divided by 7. So you basically work out the sine value and the cosine value of each of these rotation degrees. And then you put them together, you have this vector. So if I choose 4 bases, sorry, if I choose 3 bases, 4, 5, 7, then I have 6 dimension vectors for each position. Okay, and this position meets all the criteria that we've asked before. So you can calculate. I mean, I've done calculation before. So this position 3 take away position 2, the difference is the same as position 4 take away position 3. So the distance is the same. So this position vector actually recalled or faithfully worked out the position differences in your sequence. So that's a really nice way of doing position encoding. So it's guaranteed that every position is unique, and then it's guaranteed that the distance between any consecutive ones or non-consecutive, but so long as that the original position difference is preserved through this encoding. Yeah, and then you can basically, generalize this into this angular, what we call it as the angular speed, right? So this angular speed is how fast it rotates. And then you're able to use this formula to work out a implementation of the position encoding. Okay, so that's the position encoding, and then once you have the position encoding, you basically add to the hidden state the source encoding, and then you get the new vector to be put in. So it's position encoded input. Right, and then transformers, you also need something called layer norm, which basically normalize your inputs into a normal distribution with, so your original input vector could be of a value distributed like that. But then after the layer norm, you have this nice distribution with a mean around 0 and then with a standardization of 1. Okay, so after the layer norm, then you have transformers. So the input, the sort sequence gets a embedding layer. So this embedding layer can be learned or can be randomly initialized or can be from a pre-trained model. And then the position encoding gets added to it. You do a fine transformation into VQK. And then we go through multi-headed attention, go through a layer norm, and then do a feed-forward neural network fully connected linear layer, and then do another norm. Again, the layer norm, you'll be able to, so you'll be able to get the states, the hidden states. Okay, so this is one block of transformer. And then remember that you could have, multiple blocks as you see necessary. I think the default one is probably six transformer blocks. And then these states can be used to do cross attention as well. So if this is the encoder, then this just becomes the input for the decoder, and then the decoder might have cross attention coming back into this KQV. Okay, so that's a very sketchy kind of intro to neural nets, attention mechanism, and then the building blocks. Any questions? I won't go through code. So the code is all available online. If you want to build a transformer from scratch, more than welcome to. And that's how you add new things into it. So for example, this multi-headed attention could introduce a graph learning layer in there. That's what graphics, or you've looked at that paper. Graphics, yeah. The semantic parsing, the text to SQL one. Yeah. So that's how they introduce new layers in there. And in terms of code, it can be fairly straightforward. It's basically learning embeddings, and you either concatenate or add or do some sort of fusion or max pooling, so the different ways of fusing the embeddings inside to get you to the next. And hopefully what you're doing in modifying these layers actually incorporate some of your understanding about your problem domain. So the problem domain, if it's connected as a graph, then you can use graph embedding to replace the normal transformer PQV block. All right. Any questions online? No?